In this chapter, we are always mentioning ideal gas law, something like this. But then, in fact, there is no ideal gas in real life. What we have in real life is called real gas. Ideal gas is just based on some simple assumption to help us to try to predict what is the behavior of the gas in real life. But then the gas is not exactly following, but just following somehow the trend of it. Then now we're going to try to look at, in fact, what is the similarity and also the difference between ideal gas and real gas. They have something the same, which is for both ideal gas and real gas, their collision with the wall of the container will be perfectly elastic. Therefore, there will be no energy lost in collision, and the gas will not cool down itself. But then there are a lot of differences between ideal gas and real gas, all based on the fact that real gas does not obey the following two assumptions of ideal gas, which is, in ideal gas, we assume that there is no intermolecular attractive forces between molecules, and also the molecules have no size in ideal gas. But then, in real gas, actually, for real gas, there are intermolecular attractive force, and the size is not negligible. Molecules have size, and therefore, at low temperature, when the molecules move slowly, because when temperature increases, then the molecules will become faster, and if the temperature decreases, then the molecules will become very, very slow, and then they tend to bond to each other due to the intermolecular attractive force, and they will condense back to liquid. For example, steam, when it is lower than 100 degrees, then the steam molecules will move slower, then they will bond to each other to become liquid state, water. Other than that, at high pressure, high density, that means the container is very, very small. Then the molecules will be very close to each other. Then their total size of the molecules becomes significant. And also because they are very close to each other, so that their intermolecular attractive force will also be significant at the same time. That is why real gas is different from ideal gas. But then, under certain situation, opposite to these two, in fact, opposite to these two, 1, 2 here, opposite to lower temperature, that is, at high temperature and low pressure, then real gas will tend to behave like an ideal gas. That is, when we look at this small section here for A, this is very similar to the curve for ideal gas, because this part have high temperature. Because as you can remember, this is PV graph, and if you have a higher graph, then temperature will increase. And this part also have low pressure, because the y-axis is P, so that we are talking about the lower part of the graph. Then this part will be very similar to the curve for ideal gas. And lastly, we are going to summarize all this into a table. The key point is you really have to focus on the similarity and the difference between real gas and ideal gas. And the key will be, when this is in low pressure and high temperature, the real gas behave like an ideal gas, and they have a similarity, which is both collision is perfectly elastic. This is not a very popular topic, so that we just have one MC here for your practice.